like storage if you run out of space. All of those same things are true in the realm of digitization. So a real digitization program has descriptive policies, selection criteria, infrastructure requirements, usage policies. So I want to get that idea across too, that when we really talk about digitization in libraries, archives, it should be thought of as more than just scanning. Okay, so with all that said, the sense that I got from what Teresa had asked me to do was to focus on the scanning for today. So that's what I'm going to do. I'm going to focus on imaging, because even looking just at imaging, there's plenty to talk about that could fill up an hour or 2 hours. I mean, you could spend the whole day just talking about imaging. So that's what I'm going to do. If anybody would like to raise any issues around any of those other things, the bigger picture of digitization, feel free. I mean, I'm happy to talk about all of that stuff. But let's focus right now just on imaging and creating digital images. So I think it's useful to start at the very basic level and just talk about what a digital image is. Because some of the things that we'll talk about later, to really understand what's happening and some of the decisions you make, it's good to just remember what the very basic structure of a digital image is, and you can go from there. So I'm not going to make this very technical, but I just want to emphasize that a digital image at its base is made up of a grid of pixels. So when you're digitizing something, there's obviously no grid in your source material, right? Your source material is, if it's a photograph, down at the very tiny level, there's little clumps of particles that are making up your image. But the idea that it's an analog photograph, it's not like this, right, at its core. So the act of digitizing is taking something that may have a kind of continuous tone from white to gray to black and fitting it into some kind of grid. And underneath the grid in a digital image, so each one of these squares is a pixel. Each pixel is represented by a number, right? So the number is what indicates the color value of the pixel. So this H here is an extremely simple digital image that is made up of only black and white. So you can have images that are called bitonal, meaning only black and white pixels, and that's it. And a lot of text documents are scanned this way. Faxes are done this way, if you think of what a fax does. White is 1, black 0, that's it. So any fuzziness, any in-between has to become either white or black. Right? So that's an extreme version. But the same kind of thing is actually happening with a grayscale image. So here's a sample idea of what a grayscale image is. I think this is designed to be a little extreme detail of a map, maybe an aerial photograph. And so you've got a bunch of different values now, not just black and white, but you can see, again, behind each pixel is just a number. So this black pixel here corresponds to 0, this very light, almost white one, 238, and so forth. So when you get into color, then you get into another level where there's often a red, a green, and a blue value for each one, and that's how you make a color pixel. But part of the point here is that to create this, some decision has to be made, and that's going to lead into how a scanner works. Some decision has to be made from the original source, aerial photograph, exactly what value each pixel becomes. Okay, everybody following that? Okay, all right. So that's what's underneath, all the digital imaging that we're going to talk about, and all the processing that you can do to images. So when you're in Photoshop and you have filters, things that sharpen, things that change the contrast, you're really just manipulating the numbers that are behind the pixels. You're kind of doing math, you could say, on those numbers. All right. So very basically, I think it's good to understand just the very basic level of how digital image is created. Again, digitizing something that's print, turning it into a digital image. There's a sensor involved, and that sensor is the thing that takes light, a reflection usually of something, and turns it into those pixel values that become the digital image. A digital camera has a sensor in it behind the lens. A scanner has a sensor in it, which is a different kind of sensor than most digital cameras, but they generally work the same way. This is the general setup of a flatbed scanner, which uses a sensor type called CCD, charge coupled device. That's not important at all. But the idea is that this sensor sits somewhere in the body of the scanner. There's a light source that's bouncing light off of your, so you put a piece of paper down, light is being bounced off the paper, redirected with mirrors, and hitting this sensor. So this whole part moves. The sensor generally doesn't move in a flatbed scanner. And that's how the capture happens. So there's a couple parts where the quality of the scan, the quality of the scanner, you can see there's a couple aspects to it. I think there's a lens usually in here as well, but you know, quality of this is pretty important. This just comes from Wikipedia's page on image scanners, which is useful if you want to get, this is, you can get any further. This is what the CCD looks like inside a scanner. And this is important because when we talk about resolution in a flatbed scanner, so we're talking about how often we're taking an image of something. So I'll talk a lot about resolution, which is usually expressed in either dots per inch or pixels per inch. So that's how fine-grained the sampling of the original thing to turn it into a pixel is. In a flatbed scanner, it's controlled by this motor which has a belt. So that thing moves, and it can move in really tiny, tiny little increments. So if we talk about 600 pixels per inch, what that means is that this is able to divide an inch of space into 600 little movements of that whole, this whole apparatus here. 600 times taking a sample of that in an inch to turn it back into these, okay? All right. Again, I mean, in some ways you could not know about any of this. You could treat your scanner as just a black box, you put something down. But I think just understanding a little bit about this can be helpful. So if you have a question, say, what's different when I scan something on a flatbed scanner versus taking a digital photograph of it? Knowing a little bit about this can help you kind of understand what some of the differences are. Okay, so let's talk about what kinds of terms we use when we talk about digital images. What are some of the characteristics of them? Because this is underlying the later conversation we're going to have about the decisions that we need to make when you're doing imaging of historic material. So this is sort of like our vocabulary around digital images. So here are some of the most important ones. So bit depth. So we actually already covered bit depth when we looked at the sample grid images, which were showing pixels. Remember that H had only a 0 and a 1. And I said it was a bitonal image. So the bit depth in that case was actually 1, because each pixel could only be 0 or 1, a real simple on or off. That corresponds to a bit depth of 1. That grayscale image, which had values from 0 to 256, is a bit depth of 8. Then an RGB image, or a red, green, blue, a color image, would be each red, green, and blue has 8 bits, 256 possible numbers. So you call the whole thing 24-bit. So that's just part of the language of talking about digital images. Resolution has to do with that sampling that we already talked about. So how many pixels correspond to a physical measurement of your source? So I threw out there like 600 dpi, 400 dpi. DPI. Dynamic range is something really important to the quality of an image that does not have a good measurement. And so it's often kind of lost in the discussion of images. Dynamic range is a function of the quality of the scanner, of the sensor, really. So when you're digitizing something. So to go back to this, how much difference in detail of different lights and darks and how color is resolved is a function of how good this sensor is. And so that can be measured, but it's usually measured by machine. You don't think of it when you talk about an image file, but that has a lot to do with the quality of the image you get. So one of the temptations around digitization is to say, if I just ratchet up my resolution as high as it can possibly go, I'm going to get a great image that's going to capture every little detail. It's not necessarily true. The dynamic range of your scanning device, capture device, has a lot to do with the quality of the image you get. Compression and file format, these have to do with the file, the actual digital file that you're creating. I'll talk a little bit more about that, but put all these together and you get the language that you use to talk about a particular image that you're creating or working with. So for example here, you could say, well, I've made this image, it's a 24-bit, there's the bit depth, RGB, uncompressed TIFF file format, uncompressed is saying what the compression is, scanned at 400 PPI, so there's your resolution. So the reason I'm putting all these out is this is just kind of the basic vocabulary of talking about digital images. Okay, this is just more of what I was saying. Important idea is that resolution doesn't automatically measure quality. So here's a quote from somebody who was talking about dynamic range in particular of scanners, and he's saying DPI is just an indication of sampling interval. It doesn't tell you anything about what size of detail the scanner could see. So your scanner could sample 600 pixels per inch, but it might not be able to see the difference between something that small. So the quality that you come out with might be just as good as something that samples half that, 300 pixels per inch. This really has to do with evaluating your scanning machines. Once you have a digital image, there's not a whole lot you can do to productively change this. So this is kind of shopping for scanners kind of information there. All right, let's talk about compression. So compression around a digital image means taking that image that comes right off the scanner and making it smaller. So the most common digital image format that probably all of us are exposed to is JPEG. So by default, you take a picture with a digital camera, it's a JPEG, unless you tell it otherwise. Most of the images you see on websites, most of them JPEGs. JPEG is a compressed image format, which means that whatever that source of that image is, in order to get it into that JPEG format, some math has been done to those pixel numbers to make it a smaller, the data smaller. It's also a lossy image compression format. And this is important, especially when we're talking about digitizing for preservation, things around that nature. What lossy means is that as a part of the process of compression, it's the compression process is literally throwing information away. And that's important to understand. Meaning that each time you take an image and you save it as a JPEG, it's going to lose more and more of the information in the image. So if you have a scenario where you take a picture with your digital camera, it's a JPEG, you bring it into Photoshop, you do something else with it, you save it again as a JPEG, maybe then you take that and you open it up again, you crop it a little more, save it as a JPEG, it's gone through